Thanks. So last talk and titled Plug and Play Task Level Autonomy for Robotics. Thanks.
Okay. So first of all, I really like the previous talk. Myself, I'm also an engineer, so I really like the concept. My name is Wertheim, and I want to present a work performed with my colleague Dan Suissa under the supervision of our advisor, Professor Brafman here. This work is called Plug and Play Task Level Autonomy for Robotics, and in 2 words, we want to make real robots autonomous, robots that are already implemented. Okay, so our agenda today, we will talk about autonomous robot development, existing systems that integrate robotics and AI planning, the gaps we found, our contribution, an experiments video with our system, and a summary. Okay, so first of all, the current state of affairs. We interviewed engineers from 2 large companies, and this is the process they described of developing autonomous robots in the industry. And this is also, as far as we know, how things are done in RoboCup and things like that. So first of all, what the robot engineers, they do, they implement basic robot skills, things like navigation, arm manipulation, object detection. And with these basic robot skills, they implement some decision-making mechanism, something that will schedule these basic skills to achieve a high-level goal. Like we see in this example, we have a robot that it can pick objects, and we wanted to clear the room from toys and to put them in a basket. But what they do, the way they implement this decision-making mechanism, they don't use AI planning. They manually write scripts that schedule these basic skills. And they say it's not simple. Why? Because robots, they are physical agents, and their basic skills, they are not deterministic. Sometimes the pick action can succeed, sometimes it can drop the object, sometimes it can miss it completely. So it's hard to write a script to reason about probabilistic actions. And more than that, the script writer, it doesn't really know the real state of the system. Why? Because robots, they receive partial and noisy information from the environment. So writing these scripts very hard. And also you need to reason about conflicting objectives. Like I want to perform the task as fast as possible, but I also want to be reliable and to prevent the risks from the robot and the environment. So writing such scripts is a challenge. And also after they succeeded to write a script and to experiment and everything is working, then all of a sudden they're telling them, you need to support another model of this robot with a different robotic arm. So they need to rewrite it because the features are different, or maybe they want to support a different environment with 2 baskets with different features. So once again, they need to write this script, and this is hard. And our question is, why don't they use AI planning? They will just describe the planning problem. If something will change, they will change the description, and it will schedule this basic skill and achieve a high-level goal. Why not doing it? So the answer is that it requires significant integration effort to integrate their implemented basic skills with AI planning, as will be explained. And our task, this is our mission, is making AI planning accessible for robotic engineers to solve real problems in the real world. So the first thing we need to do is we need to decide on a planning model. We need to think what are the important things that we want our model to cover, because there are different formalisms to cover different aspects in planning. And the things we are thinking are important in the context of robotics are probabilistic actions that we want to be able to describe and to reason about, the partial observability of the world, and to receive noisy sensing from the world. And we also want to describe concurrent actions, like a robot that is navigating and also it's directing his camera and taking pictures. So concurrent actions are important in the robotic domain. And the model we selected is a partially observable Markov decision process, POMDPs. They don't support concurrent actions, but they do support the rest. In POMDP, the agent is not fully aware of the environment. It only maintains a belief state over possible states. And then it can select probabilistic actions. And then it receives, you can say, the outcome of executing this basic skill, and to update its belief state, this distribution over possible states. So after selecting our planning model, we need to find a way which is comfortable and good for the engineers to describe their planning problem if you want them to use AI planning. So there are two ways to do it in general. One is an exhaustive description of the problem, but this is of course not scalable, because if you want to describe the whole state space and the transition between states, even if you have 10 Boolean state variables, then already the transition function will be a table of around 1 million cells. So this is not practical. What do people actually do? They use action description languages. And in here we can see an example of RDDL. It's an action description language to describe POMDPs. And this is the transition function that compactly describes the wildfire domain. And here we have a fire that can spread to neighboring cell and want to prevent it from reaching a target cell. And it's very expressive language. You can describe if-else conditions, and you can describe probabilistic actions by sampling from common distribution like a Bernoulli distribution here. So we have something good. Maybe we can describe in real robotic problem, the engineers will describe it using RDDL. Why not? But we have a claim. We think that current ADLs, they are not expressive enough to describe real world robotic domains. And I will give two examples, but the problem is deeper, just to give you the feeling. Let's say that I want to describe an external event and the behavior of this external event, that what it does, it invokes fire in one of the cells. And what it does, it's continuously sampling a random cell from this grid. And after it finds a sampled cell that meets a certain condition, let's say it has fuel and it's not burning, then it makes it burning, and this event terminates. Sound reasonable, but you cannot describe it in RDDL. Why? Because the very basic yet needed control structure called a while loop, they don't support it. So you cannot compactly describe such a thing, and you cannot, it's hard to describe such thing. And another example from the things that we can see in the real world, let's say that in this domain, what they do, they describe the neighboring cell, and the fire can spread to the neighboring cell. But let's say that the fire can spread by the direction of the wind and the strength of the wind. This is what happens in the real world. So the fire can spread to neighboring cell, but by a dynamic neighboring. And this cannot be described in RDDL. Why? Because they don't support linked lists. And these are things we know from programming, but they don't exist in action description languages. So the expressive power, it's one thing. The second thing is that there is an abstraction gap between the low-level code and the models we are using for AI planning. If I'm deciding to trigger an action to put out a fire from a certain cell, then still I will need a mechanism to translate this action to something that will invoke low-level code of this basic skill. And so something here is missing, and again, it's causing an integration effort, and this is why robotics, they don't use AI planning. And what we saw is that probabilistic programming languages, they can compactly describe complex probabilistic models. And what we think is that we need an action description language which is powered by a general purpose programming language, more specifically C++. Why is that? Is because these languages, they are used to solve real problems in the real world, and we want to use their expressive power to describe the planning problem. C++ is widely used to implement basic skills in robotics by robotic engineers. It has a large set of implemented code for constructing and manipulating data structures, and we think it's appropriate to use it to describe the planning model. So let's look at what we have if I'm a robotic engineer and I want to use the current available systems. So the first system that was introduced is ROSplan. ROSplan supports PDDL. It's a formalism that can describe deterministic actions. But again, if in the real world something unexpected will happen, I will need to perform replanning. So this is a drawback. They also have an extension for RDDL with the limitation that RDDL can basically can describe POMDPs, but they have a limitation that they cannot describe noisy sensing of the world or partial sensing of the world. So if something unexpected happened, then you are planning based on the wrong state of the world. The robot is not seeing the real world and it's planning according to it. So this is a drawback. We experimented with the system. We can say it's a good system, but it requires significant integration effort for engineer between your implemented robotic skills and the system itself. So we think it's a good system, but it has its drawbacks. There is the CLIPS executive system. Now this system has a goal reasoning mechanism in the form of a predefined high-level goal tree, that you have your goals that you want to reach, and each goal that you want to reach, you are using a PDDL planner to pursue this goal, and by the outcome of executing this plan, then you know how to traverse in the tree and to pursue the next goal. And this system, it won robotic competitions, but again, it can only describe PDDL, which it means deterministic actions. And the last system, which is it has a nice specification to specify robotic skills, and they also integrate, and they also have auto generation of code that assists the integration phase, which is important, but it's not perfect. The user still need to write code to stitch between his skills and the systems and the system. And they also use PDDL, which means again deterministic actions. So what are the gaps we found? We think that current action description languages, they are not expressive enough for real world robotic domains. We also look at the gap between AI planning and the real world code, the low level code, and we see a gap here that needs to be bridged to reduce the integration effort. Available systems, they require users to write code to stitch between the basic skills and the user. Once again, additional integration effort. Current systems, they use planning models that don't support probabilistic actions, and the ones that do support, they don't support partial and noisy sensing. Now, these are key characteristics in robotics that you don't really know in a perfect way the environment. And we also think that a solution shouldn't be tightly bound to any specific robotic system. Today you're using ROS, which is the most widely one. Tomorrow it's Internet of Things or a different framework. So we don't want to be tightly coupled system. So what is our contribution? We introduce the autonomous robot operating system. Now, this is a plug and play solution to integrate implemented basic skills with AI planning. The only thing the user need to supply is documentation of every one of his basic skill and what are the objectives he wants to achieve. And this system, it auto-generate all the code that needs to stitch it between his skills and the system, and it schedule his code. So the user needs to document every one of his basic skills, and there are two formalisms to do it. One to describe the high-level behavior of the basic skill, and we introduce our ADL, which is C++ powered. It's called the Generative Skill Documentation Language, GSDL, and also an expressive abstraction mapping to document between the low-level code and the planning model. There is an additional environment file to describe what are the objectives of the robot and the possible state variables. Here is an example of a documentation of the abstraction mapping, how the user can document on how to activate his low-level code. He needs to document it so the system can auto-generate a middleware component that connects the low-level code and the system. So in here, it describes how to activate a ROS service. This is a ROS process, and it simply defines how to activate the low-level parameters. The abstraction mapping also translates the outcome of executing this code to something that the AI planner can reason with. And in this example, we are seeing we have two possible examples. One is success and the other one is fail. And it has a Python code that can describe the condition of sending each one of these outcomes. And this code can also use a concept called local variables. This is a concept we introduced. Now, these local variables, they are instantiated per skill execution, and they receive their value either from the response from the basic skill code or from the abstract model used for planning, or they can listen to public data published in the robot framework. And what we're seeing here in this example, we're seeing a local variable called goal reached, and this will decide whether this navigation action was successful, and it listens to public data published in ROS. It's called the ROS topic, and it has an initial value, and then you can document in a function which is very expressive on what happens, and if this topic published goal reached, and this is what's going on in ROS when you are activated, if you are using the move base, then this variable will receive true, and you can decide, you can map the low-level code to something more abstract. We also we have our GSDL to document the high-level behavior of the basic skill, and in here we are using C++ to document in a high level what will happen, how the variables will change, and in here we can see the transition function that the robot discrete location, it will reach the desired location, and there is a condition, you are sampling from a Bernoulli, and it has 10% chance of failing. You can write a list of this kind of C++ expressions. You can also describe the cost of applying such a skill. In this case, the reward is, it will be the cost, the distance of navigation. You can easily describe this function. And the model response, this is the observation that will received from the basic skill. And in here, we can describe noisy sensing, because we are saying if the action failed, then there is 80% chance that we will actually receive from the model a failed observation. Otherwise, it will be a successful observation. So we can also describe easily noisy sensing. Let's look at some experiments. What we will see here, it's a Panda robot. We have one in our lab, and we first of all we wanted to see that the integration is easy. So this is a tic-tac-toe game between a robot and a human, and we implemented two basic skills for this robot. One, the robot can draw a circle in each one of the grid cells, and the other one, the robot can detect changes in the tic-tac-toe board. And we just documented them using GSDL and AM, and we documented in the environment file what are the desired state and the undesired state, and we can see that the robot is acting in a sensible way. But the thing is, it was the whole integration phase. It took us 1 day to document the skills and to perform the experiment. So the integration was easy. Now, in this example, the actions are deterministic. So it's more easy to describe. And in here, this is the armadillo robot. We have a real one in the lab. Now we'll see a gazebo simulation. And in this experiment, the actions, they are probabilistic and noisy. We have in here a pick basic skill, and this skill can succeed or not. And when it fails, it can drop the can, so we can't pick it then. And it can also miss it completely. Then you can try again to pick it. And also after the execution, it can give you a noisy sensing whether it was successful or not and what was the outcome. And it was very easy for us to describe it. And also we performed experiments to see what is the model, to describe it easily using C++. If something changed, it's easy to change. And we are seeing we are getting a sensible behavior. It was easy to document. So to summarize, we introduced the AOS. It's a plug-and-play solution for task-level autonomy. We introduced the GSDL, which is a C++ powered action description language. And we introduced also the abstraction mapping. This documentation, it bridges between low-level code and the abstract model used for planning. For future work, we want to conduct a user study on the AOS. There is work in progress in anomaly detection with the system. And we also want to improve the documentation given by the user based on the experience the robot gained using machine learning. So we want to learn, improve documentation, and to support multi-agent planning. Thank you very much. Questions?
Thanks. Are there any questions? Thank you for your talk. Very interesting. Can you share a little bit about the kinds of anomalies that you're thinking of addressing?
We have Ronen here, and this is a work performed by another student in our group, and I'm sure that Ronen can elaborate on this.
So, okay, so most of the model that are described is a high-level model, but you can all, because there is information associated with every skill, so basically
you can associate not only the high-level information, but also low-level information. So what we do is, as you operate the robot, we record information about what's happening in the platform, in ROS. Things like resource consumption, number of messages sent, their size, and things like that. And then we use standard anomaly detection algorithms to detect when the behavior observed is different than what we've recorded in the past. So this is a low-level statistical anomaly detection that is performed together with while you're executing the plan. There is also high-level monitoring that is done. Because we have a probabilistic program basically running, we can compute the probability of events that occur. And then you can compute, this is at the model level, you can compute what is the probability of what you've just observed. And then you can raise a flag if the probability of what you've seen is very low with respect to what you expect. You get that for almost free because you have a probabilistic programming language that can do inference.
And I will just add something technical. These local variables that were described, that they describe something high level about what's going on in the low level. Every change in the local variable, it is saved in, we have a database for statistics. So we are constantly saving what's going on in the system. We can define abstract states, and then we are using it for the anomaly detection. So,
thank you. Thanks. We'll start with questions. Yeah. Welcome.
Yeah, it's probably due to my lack of knowledge, but I will guess one of the reasons not to use AI planners by default is that looking for a plan can be very expensive. So if you want to ask a robot, whenever there is a failure replan, it sounds like you're asking for a lot of resources. And depending on what kind of robot you have, you might not have these resources to just keep replanning whenever something strange happens.
yes, this problem is part of the gap we identified, that when you are using, when you are only planning based on a single state, then you can be wrong, and then you need to perform replan. But when you are maintaining a belief state, then you are not replanning, because always you are planning based on a distribution. So maybe I'm in this situation, maybe the observation was noisy, so I don't need to perform replanning, because I'm always planning based on a distribution of possible states.
Let me also add that there is a lot of solvers for POMDPs that have been used in the past in robotics and are used. So you can actually, of course, it depends on the domain, but you can actually pretty quickly generate the solution to. So we use two solvers. We have the ability to use two solvers right now. It's just an integration issue with solvers, and they can return an answer within seconds or fractions of seconds. Actually, some of them are anytime solvers because they're online solvers. So you can basically decide how much time you need for the solution process. And if you think about most robot operations, say in service robots, you have a few seconds for the decision.
And sorry, that the general concept here that you have one way of describing the documentation is so rich because you're using C++ and you can describe complex problems. And then behind the scene, the engineer doesn't even know what we are using, because we now will support DeepRL or whatever we use behind the scene. Maybe his problem, it's not a POMDP, it's only an MDP, but he has one way that you can describe complex domains, and behind the scene we can see what is the real complexity of the problem and to use the appropriate planner. So I think it gives a good answer for the robotics. For in our development, in our research, the engineer is in the center. Thanks.
Thanks. So let's thank the speaker again.